Welcome to this lecture on sensors. In the last class we looked at trajectory, and then slowly we are moving towards control systems, and we'll try and understand how a robot actually works. So there is a controller, there is a motor, and the motor rotates, and because of which the joint rotates, and due to which the end effector moves. So as we move towards control systems, or before we come to control systems, we have to study about sensors, actuators, what gives the power to the joint to move, okay, and what senses what is the present position of the joint. So we'll start off with sensors, then we'll go to actuators, and then we'll go to control systems. So today's topic is sensors, and let us try to understand very clearly how a robot actually works. So we have a robot which is here. It has a number of joints, okay, and this is the end effector. Now I want to go from position 1, this is my position 1, I want to take it to position, let's say some other position somewhere here, okay, somewhere there I want to take it, okay. This is my position 2, okay, so this is my theta 1, this is my theta 2, and this is my theta 3. So basically I want to go from from position 1 to position 2. So what the controller basically does is it finds out the difference between theta 1, let's say it is theta 1 dash here, theta 2 dash here, and theta 3 dash there. So it is theta 1 dash minus theta 1. It generates an error, okay, and then drives this error towards 0. Okay, so now basically what we are seeing is that for the controller to function, it needs to know where is the present position of the joint. So it needs to know the present position of the joint. Without knowing the present position of the joint, it will not be able to know where it is and in which direction it should go. So it should know the present position, and it should also know the final position. Okay. Now without knowing these two, it will not reach the destination. And how it finds out the present and the final position is essentially by using sensors. Okay, this is how it works. Now, so this is where the need for sensors come in. That where is the robot location at a particular instant? The controller needs to know, and it senses the sensors feedback in order to know what is the current joint angle of the robot. Now, in order to move it, it needs actuators. Okay, so it needs actuators to move the joint, to make the error del E equal to 0. Okay, so it needs actuators also. So in order for the robot to work, it basically needs sensors, actuators, and there is a controller which actually controls the robot. Now, I explained in the last couple of classes that there is what is called the independent joint control, and there is a motor, there is an encoder, which is a position sensor, and there is a gear in front. Okay, and each of the joints has one of these units, and this is basically how the robot works, and it is called independent joint control, which means that the joints are controlled in making the assumption that each joint does not affect the other joint. Now we know from dynamics that that is not true. Okay, so we make the assumption that this is a linear, okay, control system, whereas in reality it is not a linear control system. So it's also very interesting to ask this question, that why does a linear control system work reasonably well to control a robot manipulator, which is actually non-linear system. Okay, as we go along, we'll see why a linear control system is able to reasonably perform well. Now let's proceed further and see the control of link speed in open loop. So basically, if you look at, now we are coming to the robot structure actually, okay, and seeing how it is going to work, or how a robot works. So far we were studying kinematics, dynamics, which is basically the mathematical part of it. Now we are coming to how it actually works. Now let's see how a robot works. For example, we have a battery here, okay, which is giving power, and this battery, depending on where the position of this, based on where the position of this potentiometer is, okay, if it is this side or it is that side, depending on that much of current is going to flow in the battery. That much of current is going to flow into the amplifier. So essentially, this is my input. Okay, this is my input, and this is getting amplified by the DC amplifier, and there is a DC motor here. Now there is a turntable which is fixed to the DC motor shaft, and we can imagine, if you can imagine, that there is a robot link end effector which is fitted there. So this is my axis, it is rotating about this axis. Okay, so this is almost like the wrist of the robot, where there is the end effector which is fitted and it is rotating about that with 1 degree of freedom. Now as we keep moving the position of this arrow, okay, by changing the resistance here, what will happen is whatever current is going through here will get amplified by the DC amplifier, okay, and then it will go to the motor and the motor will rotate. So this is one way of controlling the speed of rotation of this motor. Okay, there is no position feedback, so we are controlling the speed. The more current you give, the faster it is going to rotate. Okay, but it is strictly in open loop. That means there is no feedback from here which is going backwards. So this is not there. So this is essentially how a robot or a motor is controlled in open loop. So what are the various devices? There is a control device which is an amplifier. Amplifier basically just amplifies the signal, amplifies the current, it does nothing else. There is an actuator, which is the DC motor itself, and there is the process, which is the turntable or a joint. So in our case, it's a robot joint, which is the same thing. Okay, so what we are trying to see is what are the various elements involved in this. So there is an amplifier which basically amplifies the current. There is an actuator, which is the motor, and there is the process, which is the turntable. In our case, is the robot joint. Now this is another control of a speed of a joint in closed loop. Now it is exactly the same, except that there is a feedback here now. So a tachometer is a measure speed. Okay, you know what's a tachometer? It measures speed. So the speed is given as feedback to this. So there is a desired speed rating, speed setting from here. There is a plus, and there is a comparator here, okay, which is a minus. So the speed is coming in from here, and this is comparing. So whatever is the desired minus whatever is the feedback, that error is coming here. So this is my error, and this error is getting amplified and is going to the motor. So if the speed set is, let's say it is theta desired, and the speed that is coming from here is theta present, okay, theta p, then this error is going to become theta d minus theta p. Okay, so it basically means that when the feedback is saying that you have reached the speed, then this error will become equal to 0. That means it is rotating at that speed. If it is falling below, then it will be increased. Okay, now if it is falling, it is going higher, it is going to be decreased. This is basically a closed loop control system, and this is how it works. Okay, this is very easy to understand. That with the feedback we have a comparator, and this comparator essentially compares the desired to the present and generates an error, and what the controller does is it just amplifies the error and gives it to the motor. Okay, so this is a closed loop control system, and again, turntable is rotating about this axis, and we can assume this to be the wrist of the robot, and the end effector is fitted there. Okay, now what are the elements involved here? So we have a control device. Okay, so there is a desired speed here, which is the voltage, and the measured speed is coming from here. It is becoming the measured speed is being sensed by a sensor. In this case, it is a tachometer, and it's coming here, and this is a comparator, which is simply doing desired speed minus present speed, generating an error, amplifying that error, giving it to the DC motor. DC motor is actuating the turntable, and this is my closed loop control system. Okay, so for the robot also it is exactly the same, because the turntable is actually you can look upon this as a joint in the robot. So what we see is that in the closed loop control system we have a feedback, and in the open loop control system we don't have any feedback. Okay, that is the basic difference. Now let's look a little further. Now let's look at, in the previous case, if you notice, there is no controller here. Okay, whatever is desired, there is a desired voltage, it generates an error, it is amplified and goes through. Now there is no controller. Now let me put a controller in there. So this is the closed loop control system for a robot, where we have a reference input, so which is my desired, let's say theta d. Okay, and there is a theta out, which is let's call it theta out is theta o. Okay, now how does it work? Let's say we have input, reference input is I want to move 30 degrees. Okay, let me take this example here, which will be easier to understand. So here is my robot. It's a single link. Okay, Now it is at, let's say, 10 degrees, just for example, and I want to move it to 30 degrees. So this is my desired, I want to move it here to 30 degrees. Okay, this is 30 degrees, exaggerated, but just as a schematic. Okay, so now what theta d is 30, that is where I want to go. Now theta output at present is 10 degrees. Okay, because at present it is at 10, let's assume. Now you can see that what is happening, the feedback is measuring, the sensor is measuring the present position of the link, okay, and it is giving it back. Now it is saying that this is 10 degrees at present. Okay, now what happens is theta d is 30, so this comparator here does theta d minus theta out, and it says it is 30 minus 10, which is equal to 20. So now 20 comes as the error, comes into the computer, and then from the computer it is amplified, okay, and then it is taken to the actuator, which is a motor here, okay, and there is a process which is my robot link here. Okay, now when 20 comes here, it is going through the computer, going to the motor. The motor is rotating, the link is rotating now, the link is going to rotate this side now like this. Okay, so what is happening is this output is changing now, it is becoming 11, 12, 13, 14, like that. As the motor is rotating the link is going closer and closer towards the desired position. Okay, so what is happening, this error is decreasing. So from 20 it is becoming 19, then 18, then 17, 16, like that, and ultimately it becomes 0. When the error becomes 0, now it knows that this fellow has reached this position now, and it switches off. So this is how a closed loop control system works. And what are the elements of the closed loop control system? One is a controller. Okay, in this particular case we have said a computer, there is an actuator, there is a robot, and there is a sensor. Okay, so we'll start off by looking at sensors, then we'll go to actuators, then we'll go to controllers, and then put all of them together to be able to understand, okay, how the full system works. So let's start off with sensors. Now another interesting thing here is that if you look at this closed loop control system, okay, the computer is basically electrical. Okay, so this comparator here actually understands electrical signals only, okay, which is the computer actually. Okay, so if you look at the input output for each of these blocks, basically the computer gives an output to the motor rotates, and once the motor rotates, the robot link moves, and the joint rotates and the link moves. Okay, now when this is moving, what is happening is energy is being consumed from one form to another. So in the electrical motor, okay, what is the input? Input is voltage and current. What is the output? Is mechanical motion, right? So in the motor we see that the computer is giving output, that output is being amplified. The amplifier is amplifying the current, giving it to the motor is rotating, which means that electrical energy is being converted to mechanical energy. Now the robot link is moving, means it is mechanical motion. Okay, the output here is mechanical motion. Okay, and this mechanical motion is coming this way. Now the computer here cannot understand mechanical motion, it can understand only electrical signals. So this mechanical motion has to be converted. So this is a sensor. So the mechanical motion has to be converted to electrical again before it can go here. So what a sensor is doing, if you look at the blocks, so if you look at one was the motor, which was the actuator, then we have a sensor. So what is the sensor block doing? The input to the sensor block from here is mechanical motion. Okay, mechanical motion or position. Okay, and what is the output? It is an electrical output signal. Electrical signal. Okay, so what is the actuator doing? It is converting energy from one form to another form. it is taking electrical energy, voltage, current basically, which is going in the windings and is rotating and producing mechanical motion. This mechanical motion is rotating the link, and then the sensor is sensing that rotation, which is mechanical motion, converting it to electrical signal and then giving it to the controller. Okay, so you can see very clearly that what are the definitions of sensors and actuators. So if somebody were to ask you what is a sensor, what is an actuator, how would you define it? So an actuator basically, actuator converts energy from one form to another. Okay, so an actuator converts energy from one form to another. In this particular case, in robotics, it is electrical energy, electrical to mechanical. Okay, but it can be other kinds of energy also. For example, it could be hydraulic. Okay, it could be pneumatic. In robotics, essentially we are looking at converting electrical energy to mechanical energy because we are using electrical motors. So that's the definition of an actuator. What is a sensor? So a sensor essentially also converts energy from one form to another. Right now, in case of robotics, what is the energy conversion? So it is mechanical to electrical. Okay. Now this gives us the very basic definition of sensors and actuators. Now, what is a smart sensor and actuator then? What is smart? This is a term very commonly used, sensor or actuator. So a smart sensor or actuator can do both conversions. What does this mean? This basically means that it can behave like an actuator or sensor as required. Okay, so smart sensors and actuators are those which can convert energy from, or they can behave like actuators or like sensors depending on what you want them. Example is a piezo crystal, piezo actuator. So in a piezo, if you give it charge, it will produce mechanical displacement, and if you give it mechanical pressure, it will produce charge. So it's going both sides. Okay, so these are called smart. So these are very general definitions which cover all kinds of sensors and actuators. Now we start off with sensors. Sensors can be classified into two groups: internal sensors and external sensors. Now in a robot, this is my robot, and every joint has a motor, okay, encoder, and a gear in front. Okay, there's a gear in front. Okay, now this encoder here is a position sensor, and this sensor essentially senses the position of the link at every instant. But a robot can have other kind of sensors also. For example, there can be a vision camera. Okay, there can be vision camera, there can be ultrasonic sensors for a mobile robot which is sensing distance to obstacles. Okay, so there are different kind of sensors which are there in the robot, and these sensors are classified based on these two groups. The first group is internal sensors. Now internal sensors are required for the basic working of the system. Now you can understand from here that the motor and the motor gear and the encoder is one unit, and the sensor here, the position sensor, is required for the internal working of the robot. Otherwise, the robot will never know where the link positions are. So without those link positions, it cannot move. Okay, the controller cannot function. So sensors required for the internal working of the system, like position sensors, velocity sensors, acceleration sensors, they are called internal sensors. Now without the internal sensors, the robot cannot function. Okay, so if the internal sensor breaks down, robot cannot function. Whereas there are other kind of sensors which are required for interaction with the environment. For example, vision, force torque sensors, then proximity sensors. So these are sensors by which the robot interacts with the environment. Now if anything goes wrong in the external sensor, for example if the vision sensor goes bad, okay, then the interaction with the environment will go down. but the robot will still function. Okay, so that is the fundamental difference between an internal sensor and an external sensor. Internal sensors required for basic working of the system. If something goes bad, then if the sensor goes bad, then the system cannot function. Whereas external sensors are for interaction with the world. Okay, interesting to note that even in the human body, our sensors are classified into internal sensors and external sensors. So internal sensors are the ones that sense things like heart rate, blood pressure, sugar level. Okay, they are required for the basic working of the body. External sensors are like vision, smell, touch, okay, hearing. Okay, they are required for interaction with the environment. Now we'll start off with internal sensors, and then we'll proceed to external sensors. Now sensors used for closed loop control basically are called internal sensors. So in a closed loop control system that we saw, you need to sense the position, you need to sense the velocity, and you need to sense the acceleration. And these sensors are basically called the internal sensors. And there are different kinds of sensors: potentiometers, encoders, LVDT, tachometers, accelerometers. These are all internal sensors. External sensors are required for interaction with the environment: touch, pressure, slip, proximity, vision. And these are like on-off switches, ultrasonic force sensors, Hall effect sensors, piezo sensors, cameras. Okay, so these are all sensors required for external interaction. So let's start off with internal sensors. So one of the most common internal sensors for sensing the position is the potentiometer. Now this is something you would have studied in high school, okay, or in college, that the principle of operation of a potentiometer. So how it basically operates is we have a coil which is having a resistance R, which is shown here, and there is a wiper here. Okay, so this is my wiper. Now the robot link is, or the robot joint is fitted onto the wiper. So the joint will be fitted here onto the wiper, and we have a resistance coil there, and the wiper can move from one end to the other end. Okay, it can. So when the joint rotates, this wiper is going to move like this. It'll here, depending on how it is rotating. And the total voltage V that is given to the main coil is V, as shown here. And you can see that the one of the terminals is also connected to the wiper. So we have a V out here. So this is my V in, and there is a V out there. Okay. So now wherever the wiper is, that much resistance is being considered. So for example, if the wiper is here, then how much voltage is going to come out? It will be a ratio of the small r to the capital R into V in. That is V out. Okay. So as this is rotating, what is happening? Small r is increasing or decreasing. When it is here, the voltage is small r will become equal to capital R. When it is here, again small r will be very small. So if you can calibrate the position, let's say at one end we say it is 0 degrees, the other end we say it is 180 degrees, then I can do some kind of calibration and say this is position or theta versus voltage. So my voltage is here, okay, or the other way around. Let's say voltage is here, so position is here, position in terms of theta degrees, and voltage is here. Okay, V volts. So for 0 volts, it will be here. Okay, one end, 180. Suppose this is 180. It is right up there. Okay, so theoretically it should be a straight line. Theoretically, but normally it will not be a straight line, but it will have a slightly curved kind of thing like this. Okay. Now why is that so? Because you know that resistance is affected by a lot of things. So it will be something like this, and this is called my non-linearity in the system, which is sigma. Now why will it not be exactly a straight line? Because resistance change is affected by, number one is by temperature. Okay, change in temperature will affect the resistance. Number two, there is physical contact at the wiper. So the wiper is contacting there. There is friction at contact. Then number three, there is wear and tear. Okay, as it is moving. Okay, so because of these reasons, it will not exactly be, voltage versus position is not exactly a straight line, and there will be some non-linearity in there. Now the potentiometer is very simple. It is used extensively by students to do experiments to measure position. It is very cheap. It's 150 rupees. Okay, but it is not used in industrial applications because of these problems. After some time it will wear off and it is not very accurate. This is the coil type. There is also a thin film type which is shown here. Principle of operation is exactly the same. Now we can also have a linear potentiometer which is shown here. The principle of working is exactly the same. R by R into V in is going to become V out. So simply by measuring V out, we can calibrate it one end to the other end, and for a particular unknown position you can see what is the voltage. Go back to this graph and find out what is the position. So potentiometers are used in labs. They're used even in industries for very simple position measurements, and they are very cheap. That is why they are used extensively. But in industrial robotics, we don't use this. Now, what is used for measuring position in industrial robots or for any industrial position measuring application is a incremental encoder. Now, this incremental encoder, as shown here, has a very simple construction. It is made of made of plastic mainly. Okay, it's a very small strip of plastic, and how it works is very interesting. That if I take the side view of this, so this is my center, okay, and if I take the side view will be something like this, okay, and there are this is a plastic ring, okay, or a strip which contains opaque and transparent parts. So there is opaque and transparent parts. So you can see this here, okay. So these white ones are transparent and the dark ones are opaque. Now on one side we have an emitter and on the other side we have a receiver. So the emitter emits light, okay, and the receiver receives light. So when the opaque part comes, there is going to be no light going through, so the receiver will not generate any voltage. Now this is essentially, receiver is something like a photocell. Okay, so when light falls on it, it produces a voltage. So when there is light, there is voltage. When there is no light, there is no voltage. So it is essentially 0 and 1. So when this is rotating, so we fix it to the joint, or this is also fixed to the back of the motor. Okay. So when it is rotating, what is happening is there is going to be the zeros and ones being produced depending on what is the amount of angle by which it has rotated. Now, so it is basically going to produce 0, 1, 0, 1, 0, 1 like this when it is rotating. Now, if there are 360 degrees, we know, for one full rotation, and there are 200 of these slots, suppose there are 200 cuts, 200 slots, okay, then your resolution is about 1.8 degrees between slots. So between any two opaque lines or any two transparent lines, the distance is going to be 1.8 degrees, which is not much. Okay, so between here and here, it is 1.8 degrees. We know that. Okay, so if you know what is the distance between this and this, between any two bits, then you know, if you know that it has gone this many times, then you know what is the total distance moved. Okay, so this is how we can measure position, by counting the number of bits which have gone through. Okay, because we know the distance between any two bits, and they correspond to the transparent or opaque sections. Now this is giving us theta. Okay, if you can count how many bits have gone through, then you can also know what is the theta it has moved through, what is the angle it has moved through. Now if you know the time of let's say this is del theta. If you know the time it took to go from here to here, then it is del theta by dt. So this is theta dot. Okay, so you know the position, you also know the velocity. Now if I differentiate this one more time, then I can know theta double dot also. Okay, so theta dot minus theta dot theta dash dot, okay, by del t, this one more time will give you the acceleration. So we can basically find the position, we can find the velocity, and we can find the acceleration. Now why this is extensively used is that if you've ever seen an encoder, it is actually just a plastic ring, okay, and it costs nothing, probably doesn't cost anything, okay, and the working principle is very simple. There's an emitter receiver on one side, and when it rotates, basically light goes through or does not go through, and it produces a signal of 0 or 1. And based on the number of bits that have gone through, you can measure, the controller knows how much distance, how much angle it has moved. Okay. Now it costs nothing. The signal that is coming out from here is 0 and 1. Okay, so the controller can actually read it. You don't need to convert it again. In a potentiometer, we need to see that the voltage that is coming out is a voltage, and the computer cannot read a voltage straight, so it has to convert it using an analog to digital converter and then read. Okay, whereas in this case it is a 0 and a 1, and a computer can straight read this. It has no problem. So it has many advantages. It costs nothing. The output can be read by the computer, and because of which this is extensively used. Any position measuring device, not only in robotics, in NC machines, in aircrafts, anywhere where you're measuring position, at the back of the motor there will be an encoder. And the basic structure is like this. So there is a motor is here, motor shaft will have this encoder here. 2 or 3 encoders in parallel. There is a gear in front. Okay, that is the construction of industrial motors that are used for robotics also. Now the two disadvantages of this are there. The first is that 360 by 200 is 1.8 degrees, which is not much. Okay, so in terms of resolution, it is not much. The second problem that comes up is that this is an incremental device. Now, being an incremental device, there is no absolute position referencing. So it can tell you how much it has moved, but this is incremental. It is not absolute. So for example, if this corresponds to 20 degrees, it has moved 20 degrees, okay, but from where? Okay, that you don't know. So to get rid of the first problem, what is done is we don't use one encoder, but we have a number of encoders which are used in parallel. So on the motor shaft, there would be 2 or 3 encoders which will be sitting in parallel. Okay, the working principle is same: emitter receiver, emitter receiver. Okay, emitter receiver, emitter receiver pair there. Now the way they are put is, if I draw it, if I see the side view here, okay, this is one encoder, if you can imagine. Okay, it has slots like this, enlarged view. There is another encoder sitting behind. Okay, and the slots of that have some phase shift. So you can see that the slots are not aligned. There is some phase shift there. Okay, so these are not aligned. There is some shift there. Okay, now because there are two, now let's call this A and let's call this B. There are two signals which are coming, 10, 10, 10, which is basically a square waveform which is shown here. So this is my signal A. It is 1 means the square top and 0 means 0. So whenever it is rotating, when the motor is rotating or the joint is rotating, what would happen is this square waveforms are going to come. Now we have two of them, A and B, and because of this phase shift, so there is a phase shift here. Because of this phase shift, the B will be lagging A. Okay, so this will come after some time. The B will come because because of this phase shift. So here first A will come, then B will come. Okay, and that is being seen here also. Now what is done here is we use an XOR gate. Okay, what is an XOR gate? So if there is any change on a signal, then there will be a corresponding change on the other signal. So any change in one signal will cause change in output. Okay, what it means is that we have signal A, signal B, both are 0, 0. At this instant, signal A is changing. Okay, so what would happen? The output is here. There will be a corresponding change on signal A XOR B. Okay, so both are 0. This is 0. At this instant, you see signal A is increasing. So there will be a change on this output signal here. Next, this is constant. This is still constant till here. Then we see that this B is changing. So the moment B changes, there will be one change here. Okay, so this means if there is any change on A or B, there will be immediately a change on this signal now. Okay, and if you see the output, you see that the wave from here to here, you have two waves out now, two square waves. So it is like this big square wave was cut into two and you have two of them. So this basically means that you're increasing the resolution by 2. Okay, so putting two encoders in parallel is going to increase your resolution by 2 by using an XOR gate. So if you have 3, you can put one more and you can increase the resolution even more. So in an industrial robot, okay, the encoders have like 1000 counts per ton, or 500 count. CPT means counts per ton. That means how many holes are there. Okay, so 1000 CPT is pretty high, so it is 360 divided by 1000. Okay, and if you have two of them, it is 2 again. Okay, the resolution is going up 2 times. So this resolution is pretty high. Okay, so it is going to be how much? 180, and it is going to be 0.18 degrees, which is pretty high because there is a gear ratio also sitting in front. Okay, so this shows that industrial robots use industrial motors which use encoders in parallel. Now, interesting question here is, how do you understand which side the encoder is rotating? Because the signal is going to be the same. Look at this figure. It is always 0, 1, 0, 1, 0, 1, 0, 1. Irrespective of the direction, whether it's clockwise or anti-clockwise, the signal will be the same. So how do you know which direction it is going? So for that, what is done is, we have 2 emitter receiver pairs. So we have 2 emitter receiver pairs which are sitting very close to each other. Okay, and because of this, there is a lead and a lag which comes in. And by looking at the lead and that lag, the controller is able to make out whether it's going clockwise or anti-clockwise. So for example, if I draw it here, this is one slot, this is another slot. So A is sitting here, emitter receiver, B is sitting here. Okay, now it knows that if A is sitting here and B is sitting here, which one is leading and which one is lagging in terms of clockwise or anti-clockwise rotation. And by doing this, it can find out where is the direction of rotation. Now, encoders are extensively used. 95% of position measuring devices are encoders because they are very cheap, they are very efficient, they work in this binary mode, and the controller can directly understand what is the sense coming. The only problem is the absolute measurement is not possible. So if you want absolute measurement, then what is done is an absolute encoder is used. Working principle is exactly same. So if I take this, the side view of this, because this is my side view. Okay, there is an emitter and there is a receiver. So emitter, receiver, and instead of one row, there are 4 rows of emitter receivers. Okay, so each one of this corresponding to one row. So this is this one, this is this one, that is that one, and that is that one. So in one shot, you get an array of signals. So it is, you get 0, 1, 0, 1, 4 signals in one shot. Okay, in the previous case, you are getting either a 0 or a 1. Here you are getting 4 of them. Okay, so this is giving you an absolute position. Why? If you look at these sectors, okay, so this could be 0, 0, 0, 1. Okay, this could be 0, 0, 1, 0. Okay, that way. So each of these sectors, either this one, this one, this one, are unique here. So the 4 bits that are going to come are going to be unique. So simply by looking at those bits, the controller can know where it is now. Okay. But this is not very extensively used because you're increasing the cost. You're putting encoders, you're putting 4 rows now. Some signal processing has to be done to decipher, to understand this output here now. So the cost goes up. So this absolute encoders, although it has an advantage of giving absolute position, it is not extensively used. Most robots, most positioning devices use incremental encoders. Velocity and acceleration sensors. A DC motor can also be used as a velocity and acceleration sensor. This is actually a tachometer. Okay, we had talked about a tachometer in the beginning of the class, and this tachometer is essentially a DC motor. So in a DC motor, if you give voltage, what happens is, this is the stator poles, which is a permanent magnet. So there is lines of force which are going through. Now, if you give voltage to the motor, what happens? It generates an EMF, and this produces a magnetic field, and the 2 magnetic fields interact, which causes the rotation. Okay, so if you give voltage input, you're getting motion. But if you give motion as an input, you'll get voltage, because this is a conductor which is rotating in a magnetic field. So it is going to have an induced EMF. So this will have induced EMF. Okay, and because of this induced EMF, we can calibrate this. Okay, so voltage versus speed. So a speed in RPM versus voltage, volts, and this should theoretically be a straight line. So once you have this calibration, if you don't know for an unknown speed here, we can simply look at this. For an unknown speed, look at how much voltage is being generated, connect it here, and then I know the speed. Okay, so this is how a tachometer works. And DC motor can be used as an actuator, or it can be used as a sensor. Now, the other kind of sensors that are used are on-off switches, emitter-receiver pairs, thermal pressure sensors. On-off switches are like the light switches that we have. So if it is pressed, it is on, and if it is not pressed, it is off. Now these are basically used for homing position. What is homing position? It essentially means that when the robot has to start, because there are incremental encoders, it doesn't know where it is. So when you start the robot, it has to go and hit one limit switch, which is homing position, or it is the base coordinate system, or we can call upon this as the 0 reference. Okay, so the robot or an NC machine, when you start it first, it homes and it finds where is the 0 of the system. So once it hits the limit switch, it knows, okay, my 0 is here, and then it can calibrate from there. Emitter receiver pairs, which are used for sensing if there is obstacles in front. Thermal pressure sensors, which are also used for contact kind of sensing. So proximity sensors are the sensors which are commonly used for sensing if there is an obstacle in front in mobile robots, or in even for serial arms for safety purposes. Okay, and how it works is very, very simple. There are a couple of inductive sensors. There are a couple of proximity sensors like inductive sensor or Hall effect sensor. Now their proximity means they don't have to touch. If it comes in near an obstacle, it will know. How does it work is very simple. So there is a magnet. Okay, this is the magnet, and there is a coil. There is a copper coil in front, which is shown here. So this is the copper coil, and there's a magnet. So in this figure, you see, because of this north-south magnet and the copper coil, there is a lines of force which go like this. Okay, that means the lines of force are not cutting the coil. Now, the moment something comes in front, that you can see here, so a ferromagnetic object has come in front, and the moment something comes in front, okay, what would happen is the lines of force will be pulled out like this. Okay, that you can see. So the moment they're pulled out, they're going to cut the coil. And if they cut the coil, what will happen? They will induce an EMF. Induce an EMF in the coil, which means creating a voltage. So here there is no voltage, voltage is 0. Here voltage will be something called V1. So the moment it sees that there is a voltage in the coil, it means that something has come in front. But of course, this material has to be magnetic or ferromagnetic. Okay, otherwise it doesn't work. Now in most industries, the parts used are magnetic or ferromagnetic. So this works very well in industrial applications. For example, if you have, when we come to applications of robotics, if you look at what is the robot applied for in industry, it is for pick and place applications, spot welding, spray painting. So in the conveyor, when a part comes, say a conveyor, a part has come, you have to sense that the part has come. Okay, so how would you sense that the part has come? So an inductive sensor can be put here like this. So the moment the part has come, the inductive sensor senses and tells the robot that the part has come. Now you can go and pick it up. So this is the application of inductive sensors. Another sensor, which is a proximity sensor, is a Hall effect sensor. And the working of a Hall effect sensor is also very simple and almost similar. So this is my Hall effect sensor, which is placed inside a north-south pole, this horseshoe kind of magnet. And if there is nothing in front, the magnetic lines of force pass like this. Means they go through the Hall effect sensor. The moment something comes in front, that a ferromagnetic material has come in front, okay, what happens? The magnetic lines of force are pulled out. Okay, so the moment they are pulled out, they become like this, and they're going out now. So here you have magnetic lines of force going through. Here they are not going through. So immediately the sensor understands that there is something which has come in front, and this is again a ferromagnetic body. It works for ferromagnetic bodies only. Another sensor which is commonly used is the ultrasonic sensor. Okay, the ultrasonic sensor is used again for sensing if there is something in front. Okay, and the working principle is very, very simple. So there is a ceramic transducer, which is a piezo. So this piezo crystal, if you give it charge, so this is a piezo crystal. If I give it charge, what will happen? It will produce a mechanical displacement. So if you give it a charge in a particular frequency, it will keep vibrating. And this vibration is the one that goes out. So there is a resin in front, and the vibration goes out like that. This vibration gets the air particles in front and produces an ultrasonic wave. And this ultrasonic wave goes out, hits something, and then comes back. Now the moment it comes back, it hits the ceramic transducer again. So if there is a pressure on the ceramic transducer, it produces a charge. So this is a smart actuator sensor. So here you can see the piezo is being actuated at this frequency. The sound wave is going out, it is hitting something, and it is coming back. The moment it comes back, it is producing a voltage again. So this is the driving voltage, driving signal. This is the return signal. Now if I know the time duration between these two signals, then I know how far the wave has gone, or where is the object in front, because I know the speed of sound in air. So depending on how much time it took to go till the object hit and come back, that will basically tell me how far the object is. Now this is again very commonly used in mobile robots. Most of the mobile robots applications use ultrasonic sensors. Today even cars in rear parking use ultrasonic sensors, and this is used by students, not only by students, even in industries, and this is very, very cheap. It's about 150-200 rupees, but very often the sensor does not see. So if you look at a mobile robot, you'll find that there will be many ultrasonic sensors sitting all around. Okay, why so many sensors are required? Why not one sensor only? Now it's very interesting that very often the sensor does not see. Now why will it not see? Now it will not see in applications, for example, or when will it see? If the ray goes out, hits the object, okay, and normally, and comes back, then only it will come back. So if the object is normal to this ray, then only it will hit and come back. Now if there's an angle, what will happen is it will hit like this and it will go off somewhere else. Okay, so objects which are at an inclined plane, or objects which have shapes where the ray does not strike normally, for example spheres, cylindrical surfaces, in those cases the ray will not come back and it will not see. So one is geometry of surface, and number two is a material. Certain materials absorb sound, say cloth, okay, cloth, wood, okay, these tend to absorb sound. So what would happen is if you're standing in front of a mobile robot and you're wearing pants, what will happen? Your pants are going to absorb this ultrasonic wave, and the robot will not see you. Okay, and third is there is a type of materials which absorb. There are particular kinds of paints which absorb. So if you don't want to be seen, you know what is to be done. So all this defense applications where they have stealth fighters and ships and aircrafts which cannot be seen on radar, they have a particular geometry, and they have a kind of material on top which actually absorbs all these rays, so they are not seen. So this is an interesting thing that a very simple 150 rupees ultrasonic sensor has such wide-ranging applications. Now let's talk about a force sensor here now. The next kind of sensor we'll look at is a force sensor. So the proximity sensors, ultrasonic, Hall effect, and the inductive sensor, they don't touch. Okay, but if you want to measure force, you have to touch. Now how do you measure force? Rather, the more interesting question is, can you measure force? Okay, so can you measure force? Okay, this is the more interesting question. So you cannot measure force directly. For example, in air, if I say, can you apply 10 newtons in air? You cannot. Why? Because there is no reaction. So you cannot measure force directly. Okay, but you can measure the effect of force. So we can measure the effect of force. Okay, so first of all, can you measure force? Can you apply force? These are interesting questions. So in air, you cannot apply force, neither can you measure force. Okay, whereas if you apply force, if there is an equal and opposite reaction, only then you can apply force, otherwise you can't. So if you measure force, you are basically measuring the effect of force. Okay, so you are basically measuring strain. Okay, so how a force is measured is, if you look at this cantilever beam. Okay, so we put a strain gauge here, one on top and one on the bottom side, and if I put a force here, what will happen is there will be a strain, and in the strain gauge, So this is the internal strain gauge, the wires, very thin wires in the strain gauge. Okay, so this is my strain gauge. What will happen because of the strain? The wires will get elongated, and if the wires are stretched, what will happen? Their resistance will change. So if the resistance changes, you can measure this voltage in and voltage out. So there is a voltage which is being given. Okay, so you can measure the change in the voltage and then figure out what is the force that is being applied. So we are not measuring the force directly, we are measuring the effect of force. So with one of these elements, how many forces can you measure? One this side, okay, and one this side, two, maybe this is one. So if I say x, this is x, and that is y. Okay, so I can measure two forces, but I cannot measure force in this direction. Okay, so with one beam, I can measure two forces. So we know that there are three forces and three moments generalized. Okay, so Fx, Fy, Fz, Mx, My, Mz. So to measure three forces, three moments, how many beams will you need? Okay, so the strain gauge essentially is made or constructed by using this kind of beam elements. So you can see there are four beam elements here. There is one here, one here, one here, and one here. And the internal construction of the sensor is something like this, as shown here. So this will be fitted onto the wrist of the robot. So this is my wrist. Okay, and the end effector will be fitted here. So this is my end effector. Okay, so if there is any force which is acting on the end effector, it is going to be transmitted here. Okay, and this is fitted onto the wrist, and in between the wrist and the end effector, you can see that these elements are there. So when a force or a moment is acting on the end effector, okay, what will happen is the strain will be caused at these locations. Okay, this will cause strain here. And if you write our force equations, so each of these beams can support two forces that we have seen. One beam supports two forces. So here if I say W1, W2 is the two forces supported by this beam, then W3, W4, 5, 6, 7, 8. So each beam has two forces. And in the center, we are having three forces acting and three moments, Fx, Fy, Fz. The direction of Fx is this side, Fy is here, and Fz is here. And there are moments which I can act about the three axes, right? So now for static equilibrium, so the forces are about, forces are acting on each of these beams, okay, right? And each, there can be a moment about an axis. So there is Mx here, My, Mz. So we have three forces and three moments which can act there. Now, for static equilibrium, we can say that sigma Fx, all forces in the x, y, and z directions must be 0, and all the moments Mx, My, and Mz must be equal to 0. Okay, for equilibrium. So if I start off by writing sigma Fx is equal to 0, then what are the forces in the x direction? If you look at this figure, so there is, where is Fx? Fx is in that direction. So what are the forces in the x direction? The forces in the x direction are, there is a W3 and there is a W7, which are in x direction. So Fx is equal to W3 plus W7. Okay. Now these are the gains. So this into W3 and W7. So these are the gains, which is, so K13 into W3 plus K17 into W7 is equal to Fx. So Fx is equal to K13 into W3 plus K17 into W7. These are the gains of the strain gauge. So if I do this for Fx, Fy, and Fz, I get three force equations. Now for moments, if I do, what is Mx? This is my Mx. Now Mx is caused by what? Mx is caused by a rotating moment, which is W4, okay, and W8. So Mx is a moment like this. So it is caused by W4 and W8. So you can see it as W4 and W8. Okay. Similarly, My and Mz. So what we see is we have three force equations, three moment equations. So you observe something more very carefully. This is 6 by 8 matrix. So it's a non-square matrix because there are 8 elements here. Okay. So it basically means that F, this matrix F is equal to K into W. Okay, this fellow is non-square. It is 8. It is 6 by 8. So we have to calibrate it. What we need to do is we need to calibrate. And how do we calibrate? We basically calibrate by putting different weights. Say some weight in X direction, 100, 200, 300 grams. See the reaction, see the voltage change in the strain gauge. and have this calibration for x, y, z, then mx, my, mz. That is the only way we can calibrate, right? So after calibration, we have to find this k matrices, the gains. Okay, so after we calibrate, basically we know what is this k, and once you know the k's, so calibrate for k's, okay, by different gains, by putting different weights. And after we do that, if you want to find what is the, for an unknown force, I'm putting an unknown force, okay, which is going to produce a strain W. So what we do need is W is equal to K inverse into F, okay. So from this equation, so I have to calibrate it. Now while calibrating, we put different forces and we see what is the strains which are coming there. And based on that, we can make a calibration charts. But here there is a problem. Now what is the problem? If you look at Fz and Mz, you see that there are 4 forces which are acting for Fx, and there are 4 of them here which are for Mz, which means that any combination of these 4 can produce the same Mz. Please note that. Similarly, Mx, okay. So suppose I have 1, 0, 0, 1, or I have 0, 1, 1, 0. Okay, they will have the same effect on Mz. Now, why does this happen? Essentially because this is a non-square matrix. So which means that if you want to find W, okay, so if you want to find W, what you need to do is you need to take the inverse of K, and the inverse of K is the pseudo inverse of K into F plus K hash K minus I into lambda. This is the solution, okay, and this is one part, this is another part of the solution, and this is essentially the error. Why? Because K is non-square, because K is 6 into 8 matrix, okay. So something to remember here is that there is always error associated with force measurements, force torque measurements. Why? Because you will not be able to calibrate and find the values of K exactly. Why? Because of this problem that for Fz and Mz, there are 4 combinations which are possible, and any of those 4 could give you the same result, okay. And this is something very important to note in force sensors, that there is error associated. And why is this error associated? Because while calibrating, they need to invert this K matrix, okay, and because K is non-square, there is a problem and there is an error here, because we are using the pseudo inverses of K. So today we will stop here, and the use of sensors also I've explained. It is basically to give the position, to sense obstacle in front, industrial applications, if a part has come, and if a part has come, it has to sense and tell the robot to go and pick it up, okay. Then we looked at force sensors, which are used for interaction with the environment. Now in the next class, we'll be moving on to actuators, and then we'll see how actuators, what are the different kinds of actuators, and how actuators actually, how they work to move the joints and then move the links. So today we'll stop here. Thank you.